In a perfectly competitive environment, every firm operates as a price taker. This means the individual producer has zero influence over the market price and must treat it as a fixed parameter. We define the firm's objective as the maximization of economic profit, represented by the Greek letter pi. This is the difference between total revenue and total economic cost. Revenue is determined by multiplying the market price of the output, P, by the chosen quantity of output, Y. On the cost side, the firm accounts for all inputs, labeled X1 and X2, multiplied by their respective market opportunity costs, W1 and W2. Because market prices are given, the firm's only levers of control are the quantities of inputs it chooses to employ. These choices are restricted by the production function, which serves as the technological boundary defining how efficiently those inputs convert into a final product. Profit maximization functions as a mathematical matching problem between uncontrollable market prices and these rigid technological limits. To solve this problem geometrically, we isolate the output y. This algebraic shift transforms our profit function into a linear equation, the isoprofit line. On a two-dimensional plane, it represents every combination yielding a specific profit. The y-intercept represents target profit plus fixed costs. The slope is determined by the ratio of factor price to output price. To target higher profits, we shift this line vertically in perfectly parallel steps. This chart overlays the production function curve onto the straight isoprofit lines. The firm's objective is to reach the highest possible isoprofit line within its technological capacity. That optimum occurs at this exact point of tangency, where the slope of the production curve matches the isoprofit line. If the market price of the output increases, the slope of the isoprofit lines must flatten. This flatter slope forces the point of tangency to slide further along the production curve, resulting in both a higher optimal input and a higher optimal output. This geometric shift explains why a competitive firm's supply curve slopes upward. At higher prices, the flattened isoprofit lines mathematically dictate a larger volume of production. We can translate this geometric intersection into formal algebraic conditions for the firm's internal decision-making. On the output side, the firm must produce until its marginal revenue equals its marginal cost. Since it is a price taker, this simplifies to producing where the market price equals marginal cost. On the input side, tangency requires the slope of the production function, the marginal product, to equal the slope of the isoprofit line. Rearranging this gives us a fundamental rule. The output price multiplied by the marginal product must equal the price of the input. Essentially, the firm hires variable inputs only until the revenue generated by the final unit of input equals the cost of that unit. However, this entire optimization framework relies on the assumption that a stable, finite tangency point actually exists. This brings us to the paradox of scale. To test the model's stability, we examine Scala-Nertrega, or returns to scale. This measures how output responds when every input is scaled up simultaneously. Under constant returns to scale, doubling all inputs yields exactly double the output. If a firm with constant returns makes a positive profit, doubling its size would double that profit. Because this can be repeated indefinitely, no single production plan can ever be considered optimal. To remain compatible with a competitive equilibrium, a firm with constant returns across all levels of production must earn zero long-term economic profit. The scenario breaks down further with increasing returns to scale. Increasing returns create a concave cost structure, where marginal costs fall perpetually. In this situation, the firm experiences increasing efficiency the larger it gets. This creates a perpetual incentive to expand. Since every additional unit produced is cheaper than the last, the firm can undercut any competitor while still increasing its own margins. This feedback loop allows a single entity to capture the entire market, mathematically forcing a transition from competition to monopoly. The stability of the competitive model therefore requires decreasing returns to scale, which create the convex cost curves needed for a localized equilibrium point. The stability of the perfect competition framework depends entirely on decreasing returns technology, which prevents individual firms from expanding into monopolies. We can also approach optimization from the perspective of cost minimization, producing a fixed target output, Y, for the lowest possible price. This requires changing our geometric perspective. We move the output variable off the vertical axis and replace it with a second input factor, x2. This convex curve is the isoquant. It represents all combinations of inputs that result in the same total quantity of output. The isocost linea, or isocost line, represents combinations of inputs that carry the exact same total cost. The slope of this line is determined by the ratio of the input prices, W1 over W2. To minimize cost, we shift the isocost line as close to the origin as possible while still touching the isoquant curve. At this tangency point, the internal technical rate of substitution matches the external market price ratio. Cost minimization is geometrically identical to profit maximization. Both seek the exact coordinate where technological trade-offs align with market prices. We translate this visual tangency into mathematical form using constrained optimization. Using the Lagrange equation, we minimize the total cost of inputs while treating the production function as a strict constraint. Calculating the partial derivatives yields our tangency condition. The ratio of the marginal products must equal the ratio of the factor prices. By solving this for every possible output level, we derive the firm's overarching cost function. The returns to scale determine whether these average costs fall, remain constant, or rise as production grows. Whether we navigate ISO profit lines to maximize output or ISO cost lines to minimize inputs, the geometric goal is the same. This entire framework is fragile. It requires firms to be bound by the inefficiencies of decreasing returns to maintain a stable market. Optimization serves as a mathematical survival mechanism, force economic profit.